Hello guys, so in this video we're going to be going over the thermochemistry. I'm going to finish up the PowerPoint and I will go through the worksheet solution. So the contents and the learning objectives we did cover in our class. Basically in this slide I have talked about sodium reaction because as you see sodium is very reactive and there is some kind of heat is released from the system. Heat is released and we say heat is written with the letter Q, and this heat shows that there is some kind of exchange of energy and this is what we study in thermochemistry, where we study the chemical energy changes in, and due to that we have a temperature changes. So the first thing first, we need to go over the first law of thermodynamics. So there's a typo over here. Law of conservation of energy. That means that energy is never lost in the universe, in the world. It just transforms from one shape to another. So we're just going to go over the stuff that we covered so far with you, counting the last semester material. So you had two hydrogen atoms, they come together and they make a bond. As you see, now we have covalent bond in here. When covalent bond happens, as you see, now we gained stability. The bond is meaning that stability. In the world, the stability is gained when you have a low energy. This is how it works in life. When you have high energy, that means that there's some instability. It's not stable. So we need to decrease the energy to gain some stability. And in chemistry, compounds, they gain stability by making bonds, by getting a lower energy level. The way it happens is that if I'll give you guys an idea over here. So in the beginning, if my potential energy was higher up here, and then this is my reactant side where I had two hydrogen atoms. They were like moving around, and then once I reached the products, there you see my potential energy dropped down when I made a hydrogen bond, covalent bond between them. So the difference in here, that it is formed, it is released as a heat to outside. So we can see that when we make the bonds, we release the heat to outside, and when we break the bonds, when we want to break the bonds, we actually input energy to the system. So the way it happens, if you break the bonds, potential energy, because it was low and stable in the beginning, because it had two bonds, like a bond between two hydrogens, and then we input energy in here. Now the products, again, two separate hydrogens outside, they are moving around. So this difference in the energy is the heat that we input into the system to break down the bonds. And essentially we gained on stability over here. So this is a good intro for us, but now we're going to move on to the more specific things. So again, you see over here this potential energy drop down when you make the bond, and this heat is released as a kinetic energy. Okay, and now we're going to talk about the system and surrounding. So most of the time the system will be in the chemistry, let's say our beaker, where we are holding a reaction mixture. This is going to be our system, and our surrounding is going to be our lab. So I gave you guys an example with the fridge, where I had a hot cup of water. It was releasing heat, and then I had this is a fridge, and then I also showed you a cup of cup of, I showed you stove, where I think in my example I showed you with the cookies, but this time I'm going to show you a cold water where the stove was heating the water. So in the first case where the fridge is the case, now we have the heat is released outside because our system is this cup with water and our surrounding is the fridge. So our system was losing energy Q to outside. Okay? Energy was transferring outside. But inside the stove, this time our surrounding, T surrounding is higher than T system. T is the temperature, right? We know that stove is going to be hotter than the system, which is our system in here, the cup of water. So the energy will be transferred inside. Q will be going inside. So in this case, T surrounding is going to be lower than T system. This is the way it happens. So our system and surroundings, since we talked about this, and now we're going to go into the more the types of systems. So we showed you one which is called open, closed, and isolated. So the open system is the one that has energy transfer and matter transfer at the same time. For example, our beaker in the lab where we're heating 100 mils of water, it was an open system. Do you remember we entered the thermometer inside and they were holding the beaker and all that? So this was an open system. And then we have a closed system where you would have a stopper in the end or something, so there won't be any kind of matter transfer to outside, but still there would be energy transfer. And that energy transfer is most of the time is like in terms of heat. So it's either heat is going outside or inside, depending if your surrounding temperature is lower than the system temperature, just like I showed you up here. So if you have for example, in our lab, we had a lamp underneath, alcohol lamp, and it was burning, it was heating the system. So Q was going from outside, right? So Q was going outside to the system, which is our beaker with the water. And then we have the isolated systems where there is no energy transfer, there is no matter transfer, and these are most of the time is like an example we have in life is like a thermos. But to be honest with you, there is no ideal system in the world. Maybe if you go to NASA and you can find some of the high-tech stuff over there where they're not, with 100% isolation and there is no energy transfer. But most of the time, you know that our thermoses over time, they become cold. So now if our system is losing energy, you see this is very important. So Q is going outside, 45 kilojoule is going outside. So our surrounding gained the energy, but our system lost the energy, okay? So somebody loses, the other one gains, right? So this is very important to keep in mind because I'm going to go in the other slides that you need to understand where some gains and some loses. So that's why one is whoever is losing, that is going to be negative energy. And whoever gains, that is going to be positive. But we will always look from the perspective of the system, and if our system is releasing energy, that means our system is going to have a negative change, and I will show you how. So there is endothermic and exothermic processes. I talked about this, the endothermic and exothermic ones. Exo means out, and then endo means in. And I have talked about you with on this where in exo the system is losing outside, and in endo system is gaining inside the system. For example, if you have a reaction where there is combustion going on, for example O2 and then CO2 and the water, because there is heat is released outside in combustion, this is going to be an exothermic reaction. Exothermic. You see, on the product side, you have a heat. That means the heat is released to outside. For example, if you have a combustion, there is going to be a fire, right? But in cases where, for example, if you have decomposition and you decompose calcium carbonate and you make CO2, in this case, you need to put the Q inside in order to break this down. You gotta provide the heat. And when you provide the heat, it's gonna be endothermic. Endothermic. And normally the way they write it, they instead of writing Q on the left side, they write it as a negative on the right side. Meaning it's going to be negative Q for endothermic and plus Q for exothermic. On the product side, if you have plus Q, that means that it is released. And if it's on the product side, it is negative Q, that means you lost to the system. You gave it to the system. Surrounding provided it. So now you can read this stuff. E out, if E out is more than E in, overall energy has been released, that is exothermic. If E in is more than E out, energy has been absorbed, and it is endothermic. So we covered this stuff in here. Now I'm just gonna go out. You need to remember exo is out, endo means in. And then now we're gonna just go revise our stuff that we covered the last term. So there's solid, liquid, and gas states. So if you remember, we had the ice, and when we need to transfer solid to liquid, we need to provide energy inside. And this is why the melting process will be endothermic, because you put the Q inside. You need to put it inside Q, like on the, let's say if you had ice cubes, and then the product is gonna be liquid, right? Liquid. You know that your Q will be provided on the left side. But when you write it down, you don't write plus Q, instead you write negative Q. And this is why it's gonna be endothermic. But when you go from liquid to gas, it is again, because you're providing, it's going to be negative Q in here, and this is endothermic as well. Now, when you go from liquid to solid, just look at here, the way I'm going to do it. Now, imagine that if we want to go from liquid to ice, I'm just going to put it inside the fridge, right? So let's say I'm going to go from liquid to ice. You see this equation in here? I'm just going to convert it. And I will write it in a different version. And this is going to be written as negative Q here. So negative Q here, and then I can just transfer the negative Q to the right side. This will be plus Q in here, which makes this exothermic process. Because you know that if you put the cup of water inside the fridge, inside the freezer, and the water will start releasing the heat to the system. Surrounding. It will start releasing energy to surrounding, and that's why you will release the energy, as you see in here. and so it's going to be exothermic. And so freezing and condensation, that's why are going to be exothermic processes. And then you can just conclude that sublimation is going to be going endothermic process, because you need to provide energy, meaning energy in gotta be more than energy out. So this is why it is endothermic. Okay, so the reactions, now we're going to go into the chemical part of it, where carbon plus O2, it gives us CO2, and the Q is the product. You see, this is all exothermic processes, exothermic. And then there is only exception. So it tells us that all of the combustion reactions, they are going to be exothermic processes. The only exception for the combustion reaction where oxygen is combining with the element, which is endothermic, is happening with nitrogen plus oxygen. As you see, it is negative Q, meaning Q will be on the left side, right? So you need to provide it to the system. This is an exception. You need to know this. And then if I just flip these reactions and I write them like this. So HNO3 instead, this is going to be reactant on this side, and I'm just writing everything down here like this. Let's write it together. So let's do the composition of HNO3. So 4HNO3 giving the product of 2H2O and then O2 and then 4NO2, right? And as you see, the Q is going to be Q was left on the left side, right? We know that it is not conventional to write on the left side. So we will transfer it to right side, where it's going to be negative Q, means that it will be endothermic. So all of these reactions are going to be endothermic because they are decomposition. They require energy input. And if you flip these reactions the other way around, you would get another exception for endothermic. This is an exothermic reaction. As you see, heat is released as the product. So now we're going to go into the enthalpy and the enthalpy change. What is the enthalpy? Enthalpy is the heat content, or you could say energy of the system. And it's written with H. And there is also heat transfer, and that is denoted with a letter Q, or which we have talked about already. So there are two different heat transfer, Q, and then heat content, which is H, which is the enthalpy, right? Enthalpy, heat content. So what happens, let's say, in an exothermic reaction? In an exothermic reaction, your heat content, we start with the reactants, and then your heat content drops down. Meaning, when they write delta H, now it's going to be H of products minus H of reactants. Okay, so currently they write it in terms of potential energy. So this is reactants, and this is product side. So as you see, in terms of number, reactants are on a higher position than products. So meaning that our system, you see, our system lost this much heat, right? Heat is transferred outside, because it is exothermic. So now when I write a reaction, I say CH4, for example, O2 gives out CO2 and a water. Let's say I released 46 kilojoule. Instead of Q, I write Q here, which is gonna be 46 kilojoule, right? 46 kilojoule. So if you deduct the number, so this difference is 46 kilojoule, right? So when you write this number, products minus reactants, as you see, because this number is lower than the reactants one, our delta H would be negative 46 kilojoule. So enthalpy change and heat, they are the same, but you just need to look which is surrounding, which is the system. So our surrounding gain this Q. That's why the heat transfer is going to be positive. But because our system lost this energy, the enthalpy change of the system is negative. So for exothermic reaction, as you see, delta H is negative, and then Q is going to be positive. You don't need to memorize this, you just need to understand. Because as you see in the graph, the product side is lower than the reactant side. And as you know, if I deduct lower number, for example 4 from 6, which is the higher number, I will have negative 2. And that's why the heat content of the system is negative, because it lost the energy, right? Lost the energy to outside. And this is Q because our surrounding gained it. Okay? And there's one condition I just need to tell you. Enthalpy change and heat equal when pressure is constant and no work happened from expansion. This stuff you don't need to exactly know until if you go to engineering and study thermodynamics, but you need to know this condition. If there was some kind of work performed, let's say with a machine or something, and there's some kind of work physically performed and the pressure changed, then the enthalpy change and the heat are not equal, meaning delta H and Q will not be equal. Okay? Like it won't be 46 and negative 46 exactly. So now I will tell you about the endothermic one. For example, in endothermic now you have products on a higher level than reactants. You see this difference, delta H is going to be equaling to Q. But because your products are going to be higher than your reactants, your delta H will be positive number, while your Q will be negative, because you know that you need to provide energy in endothermic reaction. For example, calcium carbonate, again, it goes to calcium oxide and carbon dioxide. So in this case, you know that for the composition reaction, you need to provide the energy, which is negative Q, right? So that's why your Q is negative in here. And your system, because your system absorbed energy, system absorbed energy, your delta H will be positive. And because surrounding lost energy to heat up this substance, Q will be negative. So basically, in endo, your delta H and Q. So delta H became positive and then Q was negative. And for exothermic, your delta H was negative and the Q is positive. And that is that. Okay, so now since we have this stuff, delta in, delta out, you can memorize, you can go. I recommend not to memorize this stuff. But the key points in here is that bond formation is gonna be exothermic. I told you, when you make the bonds, you gain stability, you drop down the potential energy. That's why you will lose energy outside. The Q will be lost to outside and your delta H will be negative. And Q will be positive. Exothermic, as you know. Everything is interconnected with each other. And then when you have bond breaking, meaning calcium carbonate, right? We broke the bonds. We made it decompose. So your system will go into higher energy level, and this is the energy that you input into the system. That's why your Q will be negative, meaning your Q is going to be written here negative, and your delta H will be positive, because as you see, your delta H, now in this case, this is a higher number, right? Higher number minus lower number. You always deduct products from reactants for delta H. H product minus H reactants. And because this is higher, let's say it is 40 minus 20, you will have a plus 20, let's say, kilojoule. Okay, that's why your delta H is going to be positive. So now, example. A chemical reaction has a reaction enthalpy of 430 kilojoule per mole. So that means your delta H is positive. Your delta H is positive 400. Is this endothermic and exothermic? Right away you know that when it is positive, your heat content increased, right? Your system increased because it's a plus. So it's going to be endothermic. And your Q is going to be negative because surrounding lost the heat. Okay, meaning your system absorbed the energy. So now when we talked about enthalpy change, we talked about heat. Now, what is the heat? Heat equals to, the formula it has is mc delta T. M is the mass, and C is here is the specific heat capacity, and delta T is the temperature difference, meaning T final minus T initial. Okay, so what is the specific heat capacity? Specific heat capacity is defined as the amount of heat needed to raise the temperature by 1 gram of substance by 1 degree Celsius or 1 Kelvin. For example, the specific heat capacity of copper is this much. As you see, the units is joule per gram times Kelvin or Celsius, doesn't matter. So different materials have different specific heat capacities. You need to know this. For example, in our lab, we did provide you those values. And for water, you need to actually know this by heart. It is 4.18 kilojoule divided by kilogram multiplied by Kelvin. Specific heat capacity is intensive property. What is that? That does not vary in magnitude with the size of the system being described. So it doesn't matter how big is your system, your specific heat capacity, C, will always be the same. Okay, so we know this stuff. Now we have QMC delta T. We have the formula. Now we have all the tools to solve the questions. So now let's get going. For example, it says that when 1.15 gram of sample of anhydrous lithium chloride was added to 25 gram of water in a cup of calorimeter. So this is calorimeter is used to measure the heat of the system. For example, in our lab, we had a beaker where we were measuring the temperature inside of the temperature change of the liquid. So our beaker was considered our calorimeter. But normally calorimeters are like a metal shapes, metals made from copper or something, and they would be super nicely isolated, so you wouldn't lose any heat. So in this case, you have 25 grams of water and the temperature rise by 3.8 Kelvin. Calculate the enthalpy change of solution for 1 mole of lithium chloride. So in here you added 1.15 gram of lithium chloride. There was some kind of reaction happened there, and the temperature has changed. So because the solution is the water and the temperature of the water has changed, when we use QMC delta T, we take into account the mass of the water. Okay? We know the specific heat capacity of the water. It is like this. It's going to be given to you in the exam. And you know that the temperature difference was 3.8, meaning that let's say it went from 21 degree Kelvin to 24.8 Kelvin. So it went from that to that, okay? And the difference is going to be delta T is 3.8 K. So Kelvin cancels Kelvin, kilogram cancels kilogram, and then you multiply everything. This is how many kilojoules you have. But bear that in your mind that this is released for 1.15 gram of lithium chloride. Now it is asking you for 1 mole of lithium chloride. Okay? So first of all, we need to find the molar mass of lithium chloride. The lithium itself is going to be, we need to check out the periodic table for the lithium. So molar mass of lithium chloride is going to be approximately 6.94 plus 35.5 for, this is chlorine, this is lithium, and this gives you around 42.394 gram per mole. Okay, so you can do just proportion here, or you can use the formula. It's up to you. So for 1.15 gram, you had 0.397 kilojoule, and for 42.394 gram, which is 1 mole, is going to be X kilojoule. And X would be just basically 42.394 multiplied by 0.397 divided by 115. And this is going to be 14.6 kilojoule per mole of lithium chloride. Now, because you know that your system lost this energy, right? Your system actually released, because you see your delta T is 3.80, meaning your temperature initial went higher and went into T final 24.8, and this is 20. This were just an example. meaning your system released, so it was exothermic, right? Exothermic. So your delta H, because you found this value, 14.6 kilojoule per mole, your delta H is negative 14.6 kilojoule per mole of lithium chloride. Okay? And your Q is going to be just a negative Q. The value you found, the value we found. This is the Q, right? Q. And then we found the X is the Q for 1 mole. Q for 1 mole. And then we say that it is negative Q because it is asking calculate the enthalpy change, not the Q. It's asking not Q, but delta H. And in this case, because we know that it is exothermic, delta H would be negative Q. Okay, so now example 2. So we have 180.0 joule of heat is transferred to 100 gram sample of iron, resulting in the temperature rise from 22 degrees to 26 degrees. Calculate the specific heat capacity of iron. So let's say you had an iron bar like this, and now you put inside heat, right? Meaning your system is an endothermic. This is an endothermic process. So your delta H is going to be positive and your Q is going to be negative, right? So you know the Q, which is your Q is right now 180, right? So 180 joule is your Q. So now if you look at the solution, you can see clearly from here is that 22 degrees Celsius to 26 degrees Celsius, you don't need to actually convert it to Kelvin as they did in the bottom. The only thing that you need to do, delta T, T final minus T initial, and this would be 26 minus 22. The difference is 4 degrees Celsius, or it is 4 Kelvin. It doesn't matter. The difference is always the same. The unit won't be different. So now that you have this, you can find, you know that Q equals to MC delta T, and your M is 100 gram of iron. So you got 100 grams, and your C, you don't know, that your delta T is 4K, so you got 4K here. Now let's convert the grams into kilograms. It will be 0.5 kilogram, and now you have, and then we convert this one 180 into 0.18 kilojoule, and now you have everything in your hand, and C would be 0.18 kilojoule divided by 0.1 kilogram multiplied by 4 Kelvin. And now you have everything you need. So your answer is 0.45 kilojoule divided by kilogram multiplied by Kelvin. So they made a mistake over here. They forgot to write down kilogram. Okay. So now we're going to do calculation of molar enthalpy change. So mass of copper sulfate solution and mass of zinc. So you see this is the solution, right? So what did they do is that zinc, they didn't really write it in here, but I'm just going to show you. So copper sulfate, it was solution. And then they had the product zinc sulfate plus copper. This is the reaction that happened. They put it inside 137 gram of zinc, and they put it 28.8 gram of solution. So they had this solution of copper sulfate, and they put zinc inside it. The change in temperature is 39, so delta T is 39 Celsius or Kelvin, doesn't matter. And taking the result, we can calculate the molar enthalpy. So it is asking us to find the molar enthalpy. But the way we do, we're going to find it according to the molar enthalpy of this guy, because the temperature is raised for this. The copper sulfate's temperature went from T initial to final, went above by 39 degrees Celsius, right? So this is a copper sulfate solution. So let's find the QMC delta T. They did it over here, so they did M is the kilogram of the copper sulfate solution. And because copper sulfate is been made by adding the water inside, so that's why they're using the water's specific heat capacity. And then they use the delta T, which is 39 Kelvin. And now Kelvin cancels Kelvin, kilogram cancels kilogram, and then you have 4.69 kilojoule. And that is going to be for 1.37 gram of zinc. It's going to give us 4.69 kilojoule. Okay, this is amount of energy released to outside. Now you want to find it for 1 mole, and then you're going to check the molar mass of zinc, which is 65.37, and then you're going to find X kilojoule. And then you do your calculation. Your Q, which is going to be 223 kilojoule per mole of zinc. And this Q, because it is released to outside, it is going to be, delta H is going to be negative 223 kilojoule per mole of zinc. Basically meaning when it's exothermic, your delta H is negative, and it automatically makes your Q negative. Your Q is positive here, but in order to make them equal, you put negative in front of the Q, so your delta H becomes like this, right? So that's why your delta H is going to be negative like here, and your Q is positive for exothermic reaction like this. And then we do one more question. So now it's telling us how much energy is obtained when 1 kilogram of ethane, which is C2H6, is burned in oxygen according to the question. So this is given us like this. So negative 3,120 kilojoule. Now this is, you see this 2 in front of this? That means this is amount of heat released. The heat is lost, you see, because it's negative, right? Q is like this, outside is, so delta H is negative Q, basically. So now that is for 2 moles of ethane, right? 2 moles of ethane. We need to first of all, and it is asking for 1 kilogram of ethane gas. So 2 mole of ethane. First, let's check out the molar mass of ethane, which is going to be 24 plus 6, and it is 30 gram per mole, right? So 2 moles of ethane is going to be, if we check out this formula, M multiplied by MM, this would be 2 mole multiplied by 30 gram per mole. Mole and mole cancels out. Now you have 60 gram. So when we write it, we're just going to write here like this. So we release this much energy for 60 gram of ethane. Now, how about 1,000 gram of ethane, which is 1 kilo, right? x kilojoule. Now you can find the answer. X is going to be 320 multiplied by 1000 divided by 60, and then 6 and 6 goes like this, and then we're going to divide 3120, and this is going to be 520 multiplied by 100, which is 520 kilojoule, and this is 52 megajoule, basically that. So when you round it up, so they did a precise, like they found exactly, but you can give us 52 megajoules, it's still fine. But when you write the delta H, you need to write it negative 52 megajoule, because you know that this is an exothermic reaction. Exothermic reaction. Your Q is, yes, your Q is 52 megajoule per kilogram of C2H6, and we can write this kilogram of C2H6 too. But your delta H is going to be negative, and you can just write like this. It's always, delta H is always negative Q. Okay, and that is that, guys. I think I'm just going to do this worksheet questions with you guys in the class, and once we cover this, so now on this one we see that this reaction has delta H negative this, we know that it is exothermic right away. Is this reaction exothermic? Yes. Calculate the amount of heat released if 2.4 gram of magnesium reacts. So you see that for 2 moles of magnesium, we have really, our system has released this much energy. Now it's asking for 2.4 grams. So first of all, let's find out molar mass of magnesium from periodic table. You can find out that it is going to be 24.305 grams. And then if you want to find out the molar mass for 2 moles, N equals to M over MM. And then you know the amount of moles, which is 2 mole. So 2 mole multiplied by 24.305 gram per mole, and this would be 48.610 gram. So you can basically write here, instead of 2 mole, you can write here 48.61 gram is this much, and 2.4 gram is going to be X kilojoule. And then from here you can find the value, which is going to be, which will be around 59.45 kilojoule. Okay, so calculate the amount of heat released. So it is asking released, right? So Q is going to be 59.45 kilojoule. Q is going to be positive, and delta H is negative, but in this case it's asking heat released, so we're looking for Q. How many grams of magnesium oxide are produced during the enthalpy change of 96 kilojoules? So again, if you look at this formula, so we check the molar mass of magnesium oxide. So roughly it will be 40.305 gram per mole. And we can see from formula it is for 2 moles, right? For 2 moles of magnesium oxide, you have released this much energy. And you can find with that is that M equals to N multiplied by MM, and then 2 moles multiplied by 40.305 gram per mole, mole cancels out. It's going to be 80.61 gram. And then you can see that from here is now it's telling that from 480.61 gram you release 1204 kilojoule. It's asking for 96 kilojoule. How many grams of magnesium produced? So X gram. So X would be 80 over 61 times 96 divided by 204, and this is 80.61 multiplied by 96 divided by, and this is going to be 6.43 kilojoule. This is the how many during the enthalpy change, how many grams of during the enthalpy change of 96. So this 96 was actually delta H meant to say negative 96 kilojoule, and sorry, I wrote it here wrong. This is 6.43 grams. That's going to be for 6.43 grams of magnesium oxide, and that is the answer for that. Okay, so how many kilojoules of heat are absorbed when 7.5 gram of magnesium are decomposed? Okay, now we gotta do it backwards. So let's write this reaction the other way around. So it's gonna be 2 magnesium. We write 2 magnesium oxide giving us magnesium and O2. And then in this case, delta H is going to be positive. Okay, this is going to be a positive number because we just flipped the reaction, right? So this is positive. So now it's asking how many kilojoules of heat are absorbed when 7.5 gram of magnesium are decomposed. Again, we know that 2 moles of magnesium oxide is 80.61 gram. So we see that from 80.61 gram of magnesium oxide, we absorb 1204 kilojoule. And then 7.550 gram magnesium oxide, the amount of energy will be X kilojoule, and then X would be 112.02 kilojoule of heat is absorbed, meaning Q is this, and delta H, Q is going to be, when you absorb the heat, the Q is going to be negative of this value. So your Q is negative 112.02 kilojoule, and your delta H is 112.02 kilojoule. But because it is asking how much heat is absorbed, this is your answer, because heat, when it is absorbed, it is negative. Heat is absorbed by the system, right? Endothermic. We said that when it's endothermic, Q is on the left side, or we write it like this, negative Q. That's why your answer is negative. Okay, so now it is asking us choose endothermic reactions, endothermic or exothermic. How about we just write them down? So we said that when it's decomposition, it is going to be endothermic. That's why it is going to be negative Q. And this is going to be positive Q because it is combustion. Now decomposition again, it is negative Q. And then combustion again, it is plus Q. And then combination again, it is plus Q. Okay? When the bonds are made, you see we made new bonds when we bring these guys together. So our potential energy dropped down, so that's why it is exothermic. Okay, choose endothermic and exothermic processes. So we already talked about this. You can do it on your own too, but if you really want, evaporation is endo, and then boiling is again endo, and then what do we have? Sublimation is endo, and then freezing and condensation is gonna be exo. You can check out, because this ones they release energy while the endo ones are absorbing energy. So I saw absorb, 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 and then this is release and release. So determine the delta H for each of the following reactions. So in this case, delta H is just asking for the sign of this. Because we know that this is combustion, we know that Q is released. When the Q is released, delta H is gonna be negative because our system lost the energy, right? And then in this case, you see they are combined. We made more bonds. So that means we again lost the energy. You see, like it dropped down, potential energy dropped. When you make bonds, new bonds are made. So this difference is going to be the Q. So our system again, delta H is going to be negative. In this case, this is combustion reaction again. So combustion always releases energy, like the fire, and delta H is going to be negative because our system lost it. Our heat content is going to be dropped down. That's why it is negative. Now this is combination again. Now they are combined. We again lost the heat. New bonds are made. The delta H is going to be negative. Okay, so now on this question, how much heat is released when 11.22 grams of water is produced via the combustion of propane? Okay, so as you see here, we have 4 moles of water releasing this much energy, right? So 4 moles of water, let's first of all find that amount. The molar mass of water is 18 gram per mole. You know this. And then M equals to N multiplied by MM. The formula, you got 4 moles, multiply 18 gram per mole, and this is going to be 72 gram. So for 72 gram of water, you release 2044 kilojoule, and then for 11.22 gram water, it would be X kilojoule, and X would be 318 kilojoule. Now, because we release it, it's going to be, Q is going to be positive 318 kilojoule for 11.22 gram of water. This is the answer. How much heat is released by burning 20.5 grams of methane? Okay. So again, you see we have 1 mole of ethane releasing this much energy, right? Combustion. So molar mass of methane is 12 plus 4 times 1, which is 16 gram. So for 16 gram, we're releasing 890.4 kilojoule. Now it's asking for 27.5 gram. It would be X kilojoule, and X would be 1530.4 kilojoule. Okay, and this is going to be, Q is going to be positive because it is exothermic. So 1530.4 kilojoule for 27.5 grams of methane, CH4. Now, how many grams of N2 are needed to make this much energy? So again, we're looking at here. So this is for 1 mole, right? So we got molar mass of N2 is going to be 28 grams because nitrogen is 14. So it is been told to us that 28 grams is releasing 92.6 kilojoule. Now we need to find out how many grams releases 550 kilojoule, and this would be X gram. This would be 166.3 grams of nitrogen. That is the amount. And then, how many grams of H2 do you need to get 155 kilojoule? This is the same question. So you see we got 3 moles of hydrogen. So molar mass of hydrogen is 2 times 1, and it is 2 grams per mole. For 3 moles, you need to find the mass of it, and then mole N times mm. 3 mole multiply 2 gram per mole. Mole cancels, and this is 6 grams. So for 6 grams, you release 92.6 kilojoule. It is asking how many grams of hydrogen we need to release 155 kilojoule, and the answer is X would be 10.04 gram of hydrogen. And then calculate the amount of heat transferred when 2.4 grams of magnesium reacts with oxygen and forming magnesium oxide. Now, in this case, you actually need to write down, you gotta be prepared for this kind of question. So it's telling us that magnesium reacts with oxygen, okay? And then it gives us magnesium oxide. Okay, and then you need to balance this. This is what do you do for balance, and this is given to you that delta H is this. Okay, now it is asking for 2.54 grams of magnesium reacts. This is the same question that we did above, but in this case we're actually started doing everything from scratch. So we got 2 magnesiums. So if we say the roughly molar mass of magnesium is 24.3, and then M is equal to N multiplied by MM, and we know that it is 2 moles. So 2 times 24.3, which is 48.6 gram of magnesium. So 48.6 gram magnesium gives us 1,204 kilojoule of energy outside, and 2.4 gram would be X kilojoule, and X would be 59.45 kilojoule. So Q would be 59.45 kilojoule for 2.4 grams of magnesium oxide. Now, how much heat is released when 5 moles of CH4 are burned? So you see for 1 mole, first of all, you need to check if everything is balanced. So for 1 mole, we see that if it's balanced, we see for 1 mole, we release this much energy. So 1 mole of CH4, we released 802 kilojoule, and for 5 mole, it will be 5 times more of that, and this would be 4,010 kilojoule, and that is that. Okay guys, I hope everything is clear now. If you have any questions, we're going to clear it out in our classes during the preparation. Thank you very much.